So yes, I will talk today about the two-neutron decay of lithium-13 and lithium-11 via the invariant mass method at RIBF. But first, I would like to remind a bit why it's the interest of studying exotic nuclei. So exotic nuclei are nuclei that are far from the stability. So on the nuclide chart, they are located close to the drip lines, and they are short-lived system that exhibit a wide range of structures, and they are a very good testing ground for the nuclear interaction and our understanding of nuclear structure. And they made it possible to have to find fundamental and universal properties of the atomic nucleus that are valid for the whole chart. They are also usually short-lived systems, which means that we have to use them and make them react as soon as they are produced, which means that we have to use the inverse kinematics technique to study them, and this study is an example of this technique. And today I will focus more on the neutron drip line side. So here in this small square that I have put on the chart, with for the neutron-rich lithium isotopes. So the lithium isotopes, and especially the lithium-11 is a canonical example of that, are halo and borromean nuclei. So a halo nucleus is a nucleus that can be modeled by a core surrounded by a halo of neutrons. So in our case, I would take the example of lithium-11. It's a core of lithium-9 surrounded by a halo of 2 neutrons, and it causes the effective radius of the nucleus to be significantly larger than the one we expect. And the 2 neutron halo nuclei have also the specificity of being a borromean nuclei, meaning that they are systems of 3 loosely bound bodies, and removing one part of this 3-body system unbounds the whole system. And it's usually represented by the borromean rings that I have put here on the right-hand side, for which if you remove one ring, the whole structure detaches. And these nuclei are very good testing ground for neutron-neutron correlations. Now, how can we study neutron-neutron correlations? There are several methods that I have quoted a few here. One can note, for example, quasi-free scattering reactions. So in this study, with this plot on the left-hand side, we study the knockout reaction on lithium-11, and here the point is to see the deviation of the correlation angle from 90 degrees as a trace of neutron-neutron correlations. But the method that will interest us today is the study of two-neutron decay of these nuclei that has been performed before on other nuclei, on other neutron-rich nuclei, such as oxygen-26, carbon-18, and oxygen-20. And what we do with these methods is that we measure the 3 decay products of the decay, so the fragment and the 2 neutrons, reconstruct correlation variables, and see, like it's exhibited here on this plot, very structures that are also hints of exotic neutron-neutron correlation. Sorry. So as far as the 2 neutron decay of lithium-11 is concerned, I will compare the study I will present now to this previous work by Smith et al. From 2016, where they have studied the decay of lithium-11 using the 3-body and 2-body decay energy spectra and the Jacobi coordinates. All these quantities I will explain a bit later what they are more precisely. And what has been done is that the decay path of lithium-11 and lithium-10 has been taken as an ansatz, and the response of all these decay paths have been simulated and used to fit the decay energy spectra. An example is here on the right-hand side. So that's what has been done here for lithium-11. For lithium-13, also a similar study in 2013 has been done. But we can see on the level scheme that there are no information about the nature of the decay of lithium-13. So whether it is, for example, direct, so directly goes to lithium-11, or sequential. And this is what I will try to present today. So the goal here was to determine the decay path of both lithium-13 and lithium-11, and extract try to extract information about the average neutron-neutron distance, which we will see is a key parameter for neutron-neutron correlations. And the method used is similar to the one I introduced before, so with 3-body and 2-body invariant mass and Jacobi coordinates. And we have compared them with simulated response functions of the detector produced with the Geant4. So my talk will be divided in 3 parts. So the experimental setup, then the data analysis focused more on crosstalk and simulations, and finally the results. So this is what RIBF look like. We can see that on this beamline there are 2 targets, primary and secondary target, and they have 2 different functions. So in this experiment, a beam of calcium-48 has been accelerated and has fragmented on the primary target made of beryllium-9. With this fragmentation, several exotic nuclei have been produced in a cocktail beam that then goes through this part called big rips, used to identify the different constituents of the beam. And then this cocktail beam hits the secondary target, in this case made of liquid hydrogen, and the reaction products all go to the SAMURAI setup that Aldrich mentioned earlier. And before detailing what is the SAMURAI setup, I will give few information about the cocktail beam. So in this cocktail beam, there was 80% of lithium-11, sorry, and then in equal part almost beryllium-14 and boron-17. The 2 reactions of interest that we are looking at are the proton knockout on beryllium-14, used to populate some states in lithium-13 and to produce the lithium-13, and the knockout on beryllium-12, which is used to create to obtain lithium-11. Now, what is this SAMURAI setup that was mentioned here? So it looks like this, and it has its name from the SAMURAI magnet, which is this big blue box in the middle. And first, as I mentioned previously, the cocktail beam impinges on the liquid hydrogen target, here in that case the MINOS system, which is a target surrounded by TPC. So what happens is that the reaction occurs in this area, which is the cell containing the liquid hydrogen, and the 2 protons, so the knocked out and the recoiled proton, they go through the TPC, and their trajectory is reconstructed by the TPC. And crossing these 2 trajectories with the trajectory of the beam, we can reconstruct the interaction vertex. After that, so we have produced lithium-13 and lithium-11, which will then decay, and the decay products will go through SAMURAI. So the fragments will be deflected by SAMURAI because they are charged particles, and will be then detected in these plastic scintillator wall, but the two neutrons that are not charged will go straight through SAMURAI and hit the nebula array, which is an array made of 120 plastic scintillators. I will focus a bit more on this detector right now, because a part that I would like to stress on the data analysis was made on Nebula, and it was the neutron crosstalk. So what we call neutron crosstalk is the fact that some one neutron event yield two signals in nebula. So we confuse them with two neutron events. We can see two different scenarios, so in which the two signals are detected in two different walls of nebula, and because the structure of nebula is two walls with two layers, like it's represented here, or the two signals are detected in the same wall, in one same wall of nebula. So for different wall events, either the signal is detected in the first wall, and then the neutron is scattered to the second wall, where it deposits again energy, or vice versa. It's first detected in the second wall and then is sent back to the first wall. Or for same wall events, the neutron deposits energy in a bar and then a bit of energy in a neighboring bar. And we also apply a cut on the data to remove potential gamma rays that interact with the scintillators and create signals. So first, same wall events. How do we make sure that they are two neutron events and non-one neutron events? So here, what we do is that we remove the hits that are too close to each other in space and in time. So this plot is dt, which is the time difference between the two hits, versus dr, which is the space difference between the two hits. And we remove all the events that are in this ellipse here, considering that they are all too close to each other to be true two neutron events. What we do is that we simulate the response of nebula, as is shown on the left-hand side. We apply the cut and see which one is the best one and gives the best result. And then we apply it on the data and see if we obtain similar results. For different wall events, it's slightly different. We consider the velocity between the target and the first hit, and the velocity between the first hit and the second hit. And we remove events for which the velocity beta 01 is larger than beta 12, meaning that for these events, the second hit has, like the preferred scenario for this hit is that a neutron has created one signal, has lost energy, and then has deposited energy again, creating another signal in nebula. And this cut would yield a straight line in this plot, but here it's slightly tilted to take into account that high energy neutrons will lose more energy in their first hit than low energy neutrons. And so everything that is on the left-hand side of this line, we remove. Now that we have seen what crosstalk is, I can go a bit more in detail into the observables that we'll be interested in. So I talked about relative energy, and relative energy is the invariant mass for three body or also two body for fragment and just one neutron, subtracted to the rest mass. And so this relative energy for three body that I show here. So if we see structures in this spectrum, it would indicate a resonance state in lithium-13. And for the two-body relative energy, seeing structures in this spectrum would mean that we populate some resonance states in the intermediate system, namely lithium-12 and lithium-10. Which would indicate, for example, sequential behavior of the decay of both lithium isotopes. Additionally to that, we consider the Jacobi coordinates, which we can see as two different parameterization of the same system. And we consider these four quantities, so ext, exy, and cos theta k, both for the t system and y system. Those two systems being the two parameterization I mentioned before. And we can infer here that for ext, for example, will be more sensitive to neutron-neutron correlation, as there is no, for example, no mass of the fragment in this quantity, and exy will be more sensitive to the decay path of the lithium isotope, as we have both masses in these quantities. I talk about decay path since the beginning, but what do I mean by that? So I mean three things, three hypotheses. So the first decay path that we call phase space, which is the decay, the simultaneous decay of the two neutrons without any correlations involved. And this decay follows the Lorentzian distribution with the parameter E as the center of the distribution and gamma as its width. We can also consider the direct decay, which is the same as the previous one, but with the neutron-neutron correlation, that we account for with the CNN, which is the neutron-neutron correlation function that can be approximated to this integral, in which there is a part W, which is the nature and the characteristics of the neutron source, and F, which is the final state interaction. And this integral is characterized by this RNN, which is the neutron-neutron distance. That is the quantity we will fit, and we will try to determine. That will then give us information about neutron-neutron correlation. And the last case is the sequential decay, which is the emission of a neutron, the two neutrons, one after the other, following two different distributions. So now that these three hypotheses have been set, I can show how we use them and the results. So this is the obtained three-body relative energy spectrum for lithium-13. As I mentioned earlier, we see structures, meaning that we populate resonance state of lithium-13. And here in this chart, I sum up the different resonance states that we propose to reproduce this three-body energy spectrum. Now that this has been set, what I will show now is how we cut slices in this spectrum. So the four different ranges that I have put here. And then in these four different ranges, we compute the Jacobi coordinates, and we fit them using either the direct decay or sequential decay contribution to see which reproduces better the data. So I will give an example to be more clear. So first, the low energy ranges, the two lower energy gates. So one below 400 kV and one between 400 kV and 1 MeV. And these are for each gate the four Jacobi coordinates that we have fitted here with only direct decay contribution, which means that and it reproduces the data pretty well, as we can see. Before going on, I would like to stress that in this previous fit here, we have given contributions for each resonance state response function in each gate, meaning that this must be coherent and consistent with the other observables that we show, as it's the same data. So here, what is fitted is is simulated decay scheme for each of these resonance states, but constrained by their contribution in the three-body relative energy spectrum. And so here we will have in the end a percentage of how much decay, direct decay, or how much sequential decay we have in each gate. And in this case, it's 100% direct. We do the same, but for high energy gates. So from 1 to 2.1 MeV and from 2.1 to 5 MeV. So on the left-hand side, we see that the Jacobi coordinates are well reproduced, but on the right-hand side, we see that there are structures in EXY and cos theta t that are not very well reproduced, meaning that maybe we need to now consider the sequential decay. So, and to see that and to constrain this sequential decay, we go back to the two-body relative energy spectrum, in which we see at low energy two peaks corresponding to two resonance states in the intermediate lithium-12, among other contributions. And from these two resonances, we can now fit the Jacobi coordinates that I showed before with this sequential contribution. And we see that now these structures for these two quantities are now well reproduced. So to sum up, for these 4 gates, I use this level scheme. So here I compare it to the one I showed before from this previous study, and here we see that we have few more states other that that are common to the two-level scheme, with the added information of which state decays with which path. And here we see that the sequential decay appear on that high energy. So this we have repeated for lithium-11, and this is the three-body relative energy spectrum for lithium-11. Here I considered these 3 gates that I show, and this time we have because lithium-11 showed strong sequential behavior, we have directly fitted as well the two-body relative energy spectrum to constrain the different resonance states in lithium-10, and then fitted again the Jacobi coordinates, which gives this for the low energy gate below 480 keV. So to read this slide, we can check the three-body relative energy coordinate on the top left corner. That is, we found the resonance state to reproduce the data that I have put here in this chart on the top right corner, and below are the resonance state in the intermediate lithium-10. And the different arrows are the different sequential contributions that have been simulated and put into the two-body relative energy spectrum, following the same color scheme. And the orange square is the direct decay of this resonance state that is also in this two-body relative energy spectrum. And these contributions have then been used to fit the Jacobi coordinates that we see here are well reproduced by our fit, by our response function. Sorry, and we do the same for the next gate around 1 MeV that we have fitted as the low energy tail of a resonance state in lithium-11 that is around 2 MeV, Here from the two-body relative energy spectrum, we see that this spectrum is fitted with only sequential decays from this 2 MeV state to several intermediate states in lithium-10. And we see that EXY and cos theta t are well reproduced, unlike, for example, cos theta y and EXT, which are not so well reproduced. So the hypothesis here to explain this is that we can see here that this R parameter for the neutron-neutron correlation is at 1.5 Fermi, which is the lowest value for the validity of the integral, the approximation that I showed previously, meaning that maybe here we have strong enough correlation so that this approximation is maybe not so valid anymore. Yes. Finally, the higher energy gate, so which is from 2 MeV to almost 3 MeV. And here it's the high energy, tail of this resonance state in lithium-11 that decays directly and sequentially towards the same resonance state as before in lithium-10. And here we notice a similar issue with EXT and cos theta y, while the two EXY and cos theta t are well reproduced by these contributions. And now I will sum all these results up by also a level scheme for each gate, showing the various direct and sequential decay with proportions of each. Okay, so what have we seen today? So for lithium-13, we managed to have a first observation of this sequential decay behavior at high relative energy. And this thanks to a three-body relative energy spectrum with better statistics and resolution than previous studies. But we see also a lack of sensitivity on the neutron-neutron correlation parameter, meaning that here that we had less information RNN than expected. And on lithium-11, we have also found and fitted the several resonance states, and also found a decay path for in the gates that I presented. What is now remaining to do? So what we can do is use ab initio calculations for the mass and the structure of these two lithium isotopes, which is a study that has already been performed for most of the lithium isotopic chain until lithium-11, and now pushing the computation, we will be able to compare it to the structure that we found for lithium-13 and lithium-11. And we can also compare our results with reaction theory that can bring us, give us some calculations about the Jacobi coordinate for both direct and sequential decay that we can directly compare with our results, which can provide us an understanding of whether the theory first manages to reproduce the data, and if those two match. Okay, so that's it for me today. I would like to thank you all for your attention, and I'm ready to answer questions.